Hello and welcome. My name is Deborah. In this lesson, we will further examine the different data types that are supported by Spark MLlib. First, we will briefly review local vectors, labeled points, and local matrices. These were covered in detail in other lessons. Also, we will review 3 distributed matrices that were covered elsewhere. All of this review provides a good foundation as we complete our look at distributed matrices with the most complex of them all, the block matrix. Throughout this lesson, the viewer is encouraged to look back at other lessons if any of the review material is not clear. So let's get started. Recall that Spark MLlib supports local vectors, labeled points, and local matrices that are generally stored on a single machine. However, Spark MLlib also supports distributed matrices that are backed by one or more resilient distributed datasets, or RDDs. Remember that the local matrix may be either dense or sparse, and that Spark MLlib supports column major ordering and row major ordering. This brings us to our current topic, distributed matrices and the 4 types that Spark MLlib supports. These are row matrix, index row matrix, coordinate matrix, and block matrix. The block matrix is covered here. We look at row pointers and column pointers in a previous lesson. We mention them here as a reminder of what they are and how they relate to matrices. Here we see the main characteristics of a row matrix, one of the 4 key distributed matrices. The indexed row matrix is the second distributed matrix covered. It is similar to a row matrix. However, the indexed row matrix uses meaningful row indices. Next is the coordinate matrix. Remember that this type of distributed matrix consists of a collection of tuples, with each tuple containing the row index, the column index, and the entry value. We have finally made our way to the block matrix. A block matrix is a distributed matrix that is backed by an RDD of matrix blocks or submatrices. Think of a matrix blocks as a subsection of our block matrix. It is defined by a tuple with 2 inputs. The first input is another tuple, containing the coordinates that define where our matrix block starts. In other words, its rows and column indices. The second input is the submatrix itself and the values that it contains. This matrix can either be dense or sparse. To create our block matrix from an RDD of submatrix blocks, we use the block matrix function. Each matrix block contributes 3 inputs into our block matrix function. First is the block's input, which represents its indices and matrix values. Next, there are the rows per block input and the cols per block input. These 2 inputs define the number of rows and columns, respectively, contained in each block. Therefore, these 2 values determine the size of the matrix. A block matrix supports some mathematical operations such as add, subtract, and multiply. These operations can be called by using add, subtract, and multiply functions. Finally, the block matrix has a validate function which checks whether the block matrix has been set up correctly. It can be called using the validate function. The block matrix is the most complex of the 4 distributed matrices that we've encountered. Let's look at a visual representation of what we just discussed. This should help to clarify the structure of a block matrix. This grid represents a data matrix that we wish to treat as a block matrix. We remember that a block matrix is comprised of a collection of blocks, as well as information on the size of those blocks. Further, a matrix block is comprised of a row and column index, as well as a set of matrix values. In our example, we will fill our grid matrix with some values. Let's also assume that the top left corner of our matrix has an index of 0, 0. The first step in setting up block matrix is to define our matrix blocks. We define the red block as having a block row index of 0 and a block col index of 0. Its matrix values are listed in a row major order and therefore look like this. We will repeat this process to create the green, yellow, and blue matrix blocks. For example, the blue matrix blocks would have index values of 4 and 4. We now have represented the entire large matrix in matrix blocks. These can be parallelized with the Spark context and used as the first parameter in the blocks matrix function. To complete the definition of our block matrix, we must first define the size of each submatrix. In our example, we define rows per block as 4 and columns per block as 4. Our block matrix is now fully defined. After completing this lesson, the viewer should be able to recall local vectors, labeled points, and local matrices. You should then be able to explain what a distributed matrix is and recall the characteristics of each of the 4 basic types, with the block matrix explained in detail. Thank you.